So there's always one nest that is not being used. The nest that's not being used is one of these vector equilibrium ones that is not being used, and one more thing. So there, I find that the way the spheres are coming together, they in effect are a vector equilibrium. I have two vector equilibriums touching one another, and one of them is a space, and the other is one of those triangles in my hand. I push on one triangle, and the whole system collapses. One action on the system changes the system. And I find that it's possible to make a large model of a great many of these triangles interrelated, and the picture you're going to see will be such an arrangement in which I made a large frame. It's a cubical frame of steel tubes, and we've suspended, stretched between the steel tubes, a set of wires. You think of a steel cube with its 8 corners. I can run a diagonal from each of its corners, of its 8 corners, down from one corner to the extreme opposite corner. Being 8 corners, they would make 4 axi that would cross at the center of the cube. I don't think I have a model of that here, but I'll draw it quickly. And the diagonal of the cube from this corner over here down to this corner here, one from this corner down to this corner here, and one from this corner here up to here, and this corner here up to here. They all go through the same center point. As there are then 8 corners paired into 4 axi, they make 4 lines, and they are then the same rods that you see here. Remembering that if I added one eighth octahedra to each of these corners, this would then become a cube. And so that going from the corners of a cube, these are the same lines that would go from the corners of the cube, one to the other. And now your eyes are beginning to orient the x, y, z coordinate systems with the 4-dimensional system, which is on these four lines which cross in the center of the vector equilibrium, or the center of the cube. Now the frame that we make is then a great big steel frame with steel tubes, and we run the first set of 4 rods, or brass wires, from one corner of the cube to the other. Then we make a set of other lines which are parallel to those, taking off from the edge of the cube's tubular edge. By making modular subdivision of the edges of the cube, we run wires down through the center and make a frame at the top with some more of the wires running, so that we have a great many of these 4-dimensional lines parallel to one another. And around every crossing in that system, every vertex where those wires come close together, they just pass one another. We just weave them close together. And as they pass one another, around them are mounted, and mounted on the wires themselves are triangles such as this, but they are, in the model you're going to see in the picture, they are clear plastic triangles. Each one of the clear plastic triangles has there is a red vector equilibrium open. Now, we don't make it convex. We simply make it just a vector equilibrium. And then you will see in the spaces between them, you will see clear plastic vector equilibriums, but collapse down into the octahedral position. And those are all interconnected. We found that it is possible to touch this system at one point, just press on any one triangle in this enormous complex of them, and just pushing on any one, what happens is that throughout the system, every vector equilibrium becomes an octahedron, and all the octahedrons become vector equilibriums, but it is a 3-way kind of an exchange, because remember, there are alternate spaces in here, and what is happening in effect is that every space is becoming a sphere, and every sphere becomes a space. Now that's a very convenient kind of an arrangement. That happens omnidirectionally. Even though you touch it you push it directionally, the system changes, the whole system changes so that every sphere is a space and every space is a sphere. Now I'm going to picture for you something that I feel is of very great importance in our thinking. I'm going to think of dropping a stone into a pool of water, a great lake here. And when I drop it, we all know what is going to happen. There will be a set of concentric waves, that is, which will open out, expand from one another. They expand outwardly like this, the waves getting bigger and bigger. There are about 3 of these waves, and they go out back till they hit some shore or something like that. There's something else we can do, and that is we could try that in milk, and we find it works in milk. And we could try it in kerosene, we find it works there. So it isn't something that is unique to kerosene or milk. The wave could be milk or kerosene or something. This begins to tell us that the wave may be something independent of milk or water or kerosene, that it is something in its own right. The next thing we do is water or milk, whatever we want, we make it water, and we're going to drop a lot of popcorn on the water, and we're going to have a few red kernels of red painted popcorns. We drop the stone, and we watch it very carefully, take a moving picture camera, and we'll see that the wave goes right out through the popcorn, which is on the surface. You can see the wave go out there all right. But if you'll mark very carefully the red pieces and aim your camera at them, you'll see that the red pieces simply go out from center of Earth, increase their elevation from the center of the Earth, and they go inwardly towards the center of Earth, and then they bow back and forth. Every time the wave comes along, they accommodate the wave by simply shuttling outwardly and inwardly, but they don't go anywhere. They don't go along with the wave. The wave is something that passes through them. And we begin to realize that the wave, as it moves through them, does not move the popcorn, nor does it move the water. Pick up a lot of stuff, so that's how we know it's there. We see water spouts in the same way. There are a great many twisters outside of the window here right now. There are many, many twisters going on, and we just don't see them because there's nothing. They haven't picked up enough so that they are for the moment invisible to us. So when we do see the twister, it's because it is disturbing something else, and it's not the air that we're seeing. Again, the same idea. Now, with any great thermometers, they lift like this, and then they begin to go outwardly up here. If you can see them from far enough away, and they're not being disturbed enough by anything else, what you discover is that they get to be twisted so that the top is opening out, and the bond's always going in. This would be an involuting torus. And you can think of the involuting torus also having a spiral motion as it rises like this, and then it also begins to pull back in on its own bottom like this. It is the one place where you see that kind of a pattern is in the great atom bombs, like the Bikini bomb. You remember then you have this enormous heat released. Fabulous amount of energy released as heat. And because it is and under enormous pressure, it immediately expands. Because it expands, it weighs very much less than any of the airs around. Therefore, it must along the rope. The knot is a wave, self-interference wave pattern, and I'm going to slide it along on the I start on the cotton rope with a knot, and it keeps sliding. All of a sudden, it goes off of the cotton and onto the nylon, and it keeps going on and around, and it becomes manila. Pretty soon I can really say, I push that knot clear around the circle, back and around and around again. I can say quite clearly that knot has an integrity of its own that is utterly independent of which kind of rope makes it visible to me. In other words, it is, again, one of these complex wave self-interference patterns. It is clearly a self-interference pattern. The rope is doing it to itself. I can open the rope and I can take it off, you say it's gone, but every time I make the same motion, same interferences, same kind of knots will reappear. So I give you the knot then as not being nylon and not being manila and not being cotton, And in fact, what reason you and I know it is manila and cotton and so forth are two ways. One by tactile feel, the other by its color. We say it looks like white, shiny nylon. It looks like kind of yellow, more or less shiny manila, and quite white, dull cotton. These are ways of triangle in that corner. I could put in the other triangles, the rest of the table, but that's a one triangle. That one triangle is then in the cube, and it is in a plane perpendicular to the axis from this corner down to the corner, this corner here. This corner down to this corner. It is, if I took this octahedron, which is an x, y, z coordinate system, I could form on each, this triangle here could be where that triangle, and I would bring all of the 8 cubes together as I've been bringing them together over here, and in respect to each of the triangular faces of the octahedron, which is 8 triangles. And I would have then, in respect to each one of these triangles, I'd have one little shaft. We made another quite large model, and you'll see it in here. And that model is a large steel cube. And we have such a triangle as this, mounted on a shaft running. We mount the cube up like that, and we have a shaft going through here, and we put a large triangle on the shaft, and we have a handle, and we rotate that triangle inside the cube. And the interesting thing is that as it rotates, could you kind of free that cord up for me? It's quite tangled up in the blackboard. In this set of pictures that we're going by here, later on we can go through them nice and slowly. And they are going to disclose all the forms you've been familiar with. Now, remember my little triangle got bigger and bigger. And then became the 180-degree triangle, and what had been the big triangle became the little triangle. That's what we're seeing modeled here. And we have good illustrations for all those basic actions. We have the sphere as a plurality of points on an equidistant in all directions. There are degrees of freedom, remember that. And we go through those models of degrees of freedom, positive, negative, tetrahedron. I'm going to go by those quite rapidly so that one can see them as we go, and to know that we have a methodical recording of all the patterning we've been looking at. The one eighth octahedron added to the cube. The saying that we can cube, and we can triangle, and we can tetrahedron. And here is the, I've just been talking about a little triangle rotating inside of a cube. There it is. For instance, those purple balls and the yellow ball inside of it. And those are the balls that can be eliminated from any one layer without in any way jeopardizing the structural strength of the system, which is invested in the tetrahedron. And those would be the components which can be knocked out, for instance, in the atoms. Going from an isotope of 238, you can knock out 2 of those isotopes and get uranium-236. And you can get it down to 234. And the electrons apparently do the same, dropping out certain numbers. There you're seeing the model of the, ready with that. Same 25 great circles in the icosahedron, but with 6 added, which do not go through the grand central stations, and that makes 31, what we call 31 great circles. Here we're folding up the triangles to form the various great circle components. That's what about the bow ties. Get the feel of it. The red ones are you see the vector equilibrium in the red squares and the red triangles. And you can see these diagonal ones here are the 12 great circles. These are the 3 great circles that cross this way. And this is the 6 great circles which cross this way. Now then, they're all together 25 great circles. Get your eye kind of familiar with that, because the next thing, I must have hit that screen. We're looking at the secondary wave here. The screen is doing that.
Maybe it's her.
In the next picture, you're going to see something quite fascinating. I hope this is the next picture. No, I'll have to go on. This goes between the points of contact of the tetrahedron and the cube. Very interesting that the tetrahedron can slide out of the cube with this. The edges are both continually congruent to each other. Forms a spline. And now it's halfway out, and we see the square center of the tetrahedron. Now the quadrangle begins to orient the other way. And the tetrahedron is almost out of the cube now. And finally it comes out of the cube. The string is now oriented that way. It used to be oriented that way on the cube, top of the cube. And now it comes out and the cube collapses because it had no structural integrity of itself. Back to another one. And it's in the sun, with very powerful sunlight behind it. And these are photographs taken through it, and you find the hexagonal complexes beginning to show out of that is, patterns that we're getting familiar with here. The concaves and convexes begin to show up in just by the optical, what I spoke about, optical uniqueness. Look, can you see through there? The planar are the faces, plus the spheres and the edges, all of them showing together. That is, I give the fractions of the spheres as they're cut through. There'll be two-frequency vector equilibrium. There's a two-frequency icosahedron, the ball knocked out. There'll be a three-frequency vector equilibrium, and the four-frequency, and so forth. We have each one of them transforming the other, and in every layer, there are always 2 points, which are right. That is, the count is always +2, whether it's in the vector equilibrium condition or the icosahedron condition. It's exactly the same number of marbles. So we know whether it's either vector equilibrium or icosahedron. We're looking at the outer layer is always frequency to the second power times 10 + 2. Why is it times 10 + 2? Microbiology occurring in the deep sea, and these are drawings made by scientists back in the Darwin days, and they form up in these are spherical tetrahedra. These are the central angles of spherical tetrahedra. These are the same patterns that tend to show up in the soap bubbles when you dip the exterior 6 wires of the tetrahedron into the soap bubble mass. It'll come out with the central angles of the tetrahedron in these central flanges. And here I see my 4 great circles. And excuse me, the three-dimensional system made up of 6 great circles in congruence is the octahedron, and in the clear plastic. So these are simply now there is chemical compounds and so forth, and into metals. Here is giving you the 2 columns that are in the polarized condition, non-polarized condition. And here we see our models here. A larger pattern. And we get then into the ability, and the tension lines, however, are always curved. They're simply they're greater and greater radius, but they never stop being radius. There's no time they are not radius, therefore they're curved. Therefore, no matter how large they are, they will finally come back upon themselves. That is, tensional lines are inherently self-seeking. No matter how many secondary precessions you get, that curved line has finally got to find itself again. So they will always close back upon themselves. Tension, then, is finite because it comes back upon itself. But it tends to be very big. Now we really get the scheme of the universe. That is, the big scheme of the coherence is in the terms of the tensionals, which are finite, do close back on themselves. And the compressions tend to get to smaller radius, and they get into be the little local. So we'll have the little planets, which are the little local compressional assemblies. Even though within the atoms themselves we find tension. There's tension all the way through the system, we said, and compression all the way through the system. These are co-functioning in and out tides of one another. But it's the big scheme, I'm just giving you one macrocosmically, where we have comprehensive tension in very large pattern and local compressionally high tide groups such as planets. The planets are very, very logical because we find in compression then, I take the cigar form and we begin to press on it begins to get bigger and bigger as equator, finally gets to be a sphere. In the condition of sphere, something unique occurs. Following the cigar, there is a unique axis of the cigar. There's a neutral axis of the cigar. When it gets to be sphere, for the first time, any aspect is neutral axis. The shape of the universe, rather than thinking of the universe as non-simultaneous, therefore not having any one shape, simply being is non-shapeable, doesn't require shape. But we were taught to think shape, and we were taught to think statically. Therefore, we were taught to think the way some of the Greeks thought about a series of envelopes of systems within systems. They'll finally get there must be the outer system. That is the way we were sort of brought into a sense of frustration by saying, where is infinity? And what is the end of the show? If we get to the last envelope, then what goes on? Well, there must be something out beyond this. And we didn't like that. That was a frustrating sense of infinity. I've given you now that our experience shows there are no straight lines, that we do get these curves, the different kinds of curves, the bigs and littles, and that the tensions do come back upon themselves. The thing is not to be considered simultaneously, but the tension gives us a finite universe, because it must return upon itself, and the big part of the universe is handled in tension, and the local big huddles are in compression. That gets to be a pretty good scheme. And I realize that the only real infinity that ever will be what I can do in the way of further local dichotomy. The dichotomies or the infinity is as long as you and I are able to ask a question, we can make another division. But the question asking, the further dichotomy is not here, make them fast, and then interconnect tensionally here, and cut this one off from this one here, which would be cut the same way. And each one will become that same threeness you're looking at up there at the top of the wall. That gets down to be the simplest one that we're able to do in the tensegrities. And then we get up into enormous complexities and say this is simply flatter and flatter tetrahedra, and they can be cut off at this point from each other, right? I can make an interior tension to complete the base lines of the octahedron up there. Now, in relation to the tensegrity, I would like to say then that I am quite confident that this is all the kind of structure there is, and that when I do this, and we're very subject to easy accounting. So we propose it's not just an even distribution of some kind of nothingness. It is actually discrete molecules. And what we've discovered about a gas balloon is, when we give it what we call pressure, is that the molecules don't want to get crowded beyond a certain comfortable range, and the outer molecules are trying to get out of the system, and they continually, actually dynamically, hit the skin. They're a whole series of punches. They're like an enormous number of fish in here who are building up terrific velocity and running into the net. We have an open net. The net mesh is too small for the fish to get out. I've got at sea an enormous net which will be let down, which is spherical woven, but as we let it down in just like this. We've got a bunch of fish in there, and they begin to keep hitting the net and begins to get spherical. That's exactly what happens in our gas bags. So it is then a net with a lot of fish in it that are very powerful hitting it. Fact is that the shape that it takes is only by virtue of the fish at the surface that hit it, not the shape. Even though there's a cause that there were others that were being crowded, but the point is that the ones that gave it the shape were only the surface set ones. So I thought it could be possible to do the following. Usually the action-reaction gets inertia of the room, the building, to shove off against. But the two swimmers could swim and meet one another at the center and shove off from one another's feet, so they get action-reaction together. So I saw that we could take our fish and then, in fact, get action-reaction pushing off from one another. And each one of them would immediately hit the net. I want to take one out near the net, and each would pair off, and each one would shove off and hit the net locally. And I found that that's exactly what we have here. These are paired fish hitting the net. Each one of those are two fish. And there's one going east and one's going west. And one of the things to know about a chord is that the center of the chord is always nearer the center of the system than are its ends. Therefore, as an angular resultant, as they hit the end, they are trying to go outwardly. The resultant of forces of these two ends pushing like this, as much as these two ends are further away from the center of the system than is its own center, the result is that these two ends are pushing outwardly of the system. They're trying to get out. The resultant forces of the two is an arrow outwardly this way. And all the tension members are continuous. And their resultant arrows are all pointing inwardly. So that what you have here is the outbound arrows neatly impinging on the inbound arrows, and we have a structural stability. And because of this, we can now throw away all the interior fish. Let them go. We don't need them anymore because of this pairing. So that we really have, in the first case, a set of fish in the center who are in effect, by crowding, really represent all the reactions in a rather random manner inwardly of the system. Now we're pairing the reactions right at the surface. We don't need the interior. Therefore, this is really a pneumatic bag. It became very exciting to realize the 10 segmented sphere is a pneumatic bag. It is a discrete pneumatic bag where the size of the molecules is exactly uniformly designed to exactly hit the network. The network is not overdone. It's not a very fine net with rather random size, lots of big fish in it, where you get a lot of redundancy, where there's more net than you need or more fish than you need. Here we have a discrete match here with exactly the right numbers of fish and exactly the right pairs. It comes through the holes very easily. But the point is there is an array of structure which is concave on the inside. There's just enough reflectivity on the inside of the system to impound radiation which will bounce around inside of it. Just the amount of radiation which it will pick up, the heating of the air locally inside it, because it does make a little network, and the air can't escape out and so forth, it simply gets heated and it gets pushed out. Because it gets hotter, somebody must expand, therefore it pushes out a little. Just, we find a 1 degree raise in temperature inside the system of a 1 miler, which in itself will bring about, will push more air out than the weight of the structure itself. Therefore, the whole system weighs less than the atmosphere around, therefore it must float upwardly. As I flew out here today, coming over the Alleghenies, it was a very good morning scene. It was a very nice clear day, but suddenly coming the Alleghenies, there were clouds. Well, the Alleghenies right now, and this should be for 10 minutes. This summarized many things for you. Bring it together.